Okay, as you can see from the top of the screen, the plan for the day, we're going to look at sets and compound inequality. There's quite a bit of stuff in today's quick little lecture, so let's jump right in. First thing, sets. What is a set? Sets are a lot of different, you've seen sets in a lot of different places. You've seen things like the set of all integers, the set of all whole numbers, the set of all real numbers, and so on. You've seen sets before. So let's talk a little more specific about some notation about sets. I'm going to call A, so I'm going to say A equals this set. That notation there means the set of numbers 1, 2, 3, 4, 5. So A is defined to be strictly the numbers 1, 2, 3, 4, 5. I'm going to define B as a set of numbers 3, 5, 7. So what some notation that we need to know is if I want to say that something is a member of a set, I can say 3 is a member of set A. That fancy little symbol there means it's a member of or an element in that particular set. I could say that 3 is also an element or a member of set B. Okay, so let's look at something else. I want A union with B. Set notation. Union is a right side up U, and what it means is it's every element that is in either A or in B. If I want to union A and B together, I want every element, every member, every, in this case, number, that is in both set A and set B put together. Notice how I shouldn't use the word and. It's in set A or in set B. Is the number 1 in set either A or B? Yep. Is the number 2 in set A or B? Yep. 3, 4, 5, 7. Basically what you are doing is you are unioning, you're putting the two together. Every element in A and every element in B come together and make one set. How about intersect? A intersect B. This is every element that is in both A and B. Number 1, is it in A and B? No. The number 2? No. The number 3? Yes. The number 5? Yes. That's it. Intersection. The elements that are in both A and B. It's called the overlap. It's where these two, it's what these two have in common. If you remember Venn diagrams back from some other class, hopefully you've seen Venn diagrams. If I call this circle on the left set A, the circle on the left set B, what goes in the middle is everything that is in the intersection of A and B. So the 3 and the 5 are in both set A and in set B. What goes out here? 7. What goes out here in the A? 1, 2, 4. Notice the circle that is set A. It contains the numbers 1, 2, 3, 4, 5. Notice the circle that represents set B. It does contain 3, 5, 7. This circle here does wrap around the numbers 3, 5, 7. But notice the 3 and the 5 are contained in both the A and the B. Notice this whole system is the union of A and B. I shouldn't have a circle around that, but I'm trying to point your attention to it. That whole set put together, A and B, is the numbers 1, 2, 3, 4, 5, 7. Venn diagrams are nice ways of looking at and describing sets. Okay. Next thing. Let's look at solving a compound inequality. First of all, let's look at graphing. X is less than 5 or X is greater than 9. X is less than 5 or X is greater than 9. There's 5. Open circle, right? Because we don't include the 5. And I want everything that is less than that. 9. Open circle, because I don't include the 9. And I want everything that is greater than that. That is a compound inequality. Why is it a compound inequality? Because it has two inequalities, and we are solving them both at the same time. Okay? What if I have this? Same one. X is less than 5, and X is greater than 9. Notice this up here is really the union, and this is really the intersection. An OR represents union. It could be in set A, or it could be in set B. This says it needs to be in set A and in set B. Well, if this number line I have graphed there is X is less than 5 or X is greater than 9, where's the intersection? What is the intersection? The intersection of that is, not a very good set notation, the empty set. There are no numbers that are both bigger than 9 and less than 5 at the same time. Another notation for that would be the circle with the line through it, called the empty set, or it's called the null set. Empty set or the null set is a part of or a subset of every set. Okay? Every set could be written as the empty set, or it's a subset of the empty set. Here's an example. What if I go back to my numbers I had, or my sets I had before? Let's say I want X to be a member of A, and I want it to be less than or equal to 0. Give me every element that is in A that is also less than or equal to 0. Here's the other fancy way of saying that. I want the set of all x's such that X is a member of A and it is less than 0. So there's a fancy way of writing that, which you need to know. Okay? X is a member of, or find every element of X such that. That little bar right there means such that. That guy there means such that. So that, something like that. So we want it to be a member of A and less than 0. That is not possible. Answer, the empty set. The empty set is an option or a subset of every set. All right, sorry, I kind of jumped around on that one. Next thing, let's do another one. Let's say X needs to be less than 9 and greater than 5. That one's going to work. I want X to be less than 9, and at the same time, I want it to be greater than 5. I want the overlap of those two, so the intersection of those two would be right here. Don't include the endpoints, so I have open circles. Include everything that is less than 9 and at the same time greater than 5. Okay? All right, let's get a little harder. So what if I wrote this? X plus 3 needs to be less than 9 and at the same time greater than 4. The notation for and, this is pretty important. The notation for and is when you put two inequality statements together as one statement. This always implies and. If you have two inequality statements, what are my two inequality statements? Well, my first one is x plus 3 is less than 9, and my second one is x plus 3 is greater than 4. If I put those together as a single inequality statement, I've just implied that it's an and. Okay? If I want this to be an or, if I wanted to say, give me every number that is both x plus 3 needs to be less than 9 or it needs to be greater than 4, I have to use the word or. If you mean to union them together, you have to write two separate inequality statements put together by the word or. If you write it as a single statement, it means and. Now, I could just simply write this as an and statement, and I'm fine. But if I put it together, I'm immediately telling everybody I mean for this to be an and statement. Both of these statements have to be true at the same time. Not or, it's an and. All right, I think I've said that enough times. So, how do I solve a compound inequality? Remember, at the very beginning of this recording, I said a compound inequality means two inequality statements that need to be solved, which is what I have. I'm going to pretend they are two separate inequalities. So I'm going to solve this guy. I don't know how to get rid of it. I need to solve that first. Then I need to solve that one. But if I think about it, it's the same steps for both inequalities. My first step is to get rid of the 3 in both statements. So I'll do the minus 3 at the same time for both statements. So I'm going to subtract 3 from all three sides. From here, and from here. Remember what we're solving. We're solving this, and we're solving this. Whoops. In both cases, my first step is to subtract 3 from both sides. So all we're going to do is just leave it as one inequality statement and just do that step of subtracting 3 from all three sides. So on the left-hand side, I get 1. On the right-hand side, I get 6, and I've got it. X needs to be between 1 and 6. On a number line, it's between 1 and 6, open circle in both cases. X needs to be greater than 1 and at the same time less than 6. All right, interval notation. How do I write that in interval notation? Endpoints, sorry, not 0. My endpoints, 1 and 6. I don't include the endpoints. So in interval notation, the answer to that would look like 1, 6 with parentheses on both sides. Okay? Let's do a couple more. I'll give you a second. If you want to hit pause, you may. All right, I'm going to solve them separately. In this case, I can't do what I did with the AND statement, so I'm just going to solve them as they are, two completely separate inequalities that are joined by the word or. So they are two separate sets, and let's just solve them. First step, add 9 to both sides. First step over here, add 1 to both sides. Next step, on the left-hand side, I'm going to divide by 3. On the right-hand side, I'm going to divide by 2. Number line. My two endpoints are 3 and 10. I want to include the 3 and everything that is less than that. I want to include the 10 and everything that is greater than that. My OR statement says it could be in this set over here, or it could be in this set over here. It's the union of the two solutions. Either set works. All right. Let's do another one. All right, if you want to hit pause, you may. Otherwise, I'm going to start. First step, if I want to get x all by itself, I can't change it now because some of you have already started. My first step is to add 2 to both sides. And, sorry, all 3 sides. Right, left-hand side, left-hand side I get 1, right-hand side I get 14. Divide by 4, I get 1/4 on the left, I get just 1 in the middle, and I get 14 divided by 4, which is the same thing as 7 over 2. Graph on our number line. 1/4 is down here. 7 halves, how big is 7 halves? 2 goes into 7 3 times with 1 left over, so it's 3 and 1/2. I want x to be greater than 1/4 and less than 7 halves. All right. I think that should take care of sets and inequalities.